Hey everybody, this is 17.6 through 17.11. We're going to be talking primarily about capacitors and the concept of capacitance. Right here you can read that a capacitor is a device that stores electric charge, consists of two conducting objects, usually plates or sheets, that are placed near each other but not touching. Capacitors are used all over the place in electronics whenever we need charge to be released sort of quickly or almost instantaneously. We want to dump the charge quickly. Batteries, if you think of them, they store charge, but they store it and they release it very slowly. Now, if you think about the use of a battery, hopefully when you put a battery into something, you're expecting or hoping that it lasts for a long time. You don't have to change the batteries regularly. Whereas a capacitor is something that when you want to release the energy from that capacitor, you want to have it happen very, very quickly. And so capacitors can work as camera flash. They also work they work as why am I struggling with defibrillators. So when you have an artificial defibrillator, bring someone who's maybe died back to life, get their heart started again. You use a defibrillator. Now a capacitor symbol is indicated by two parallel lines with the leads. These are the electric leads coming off of it. Depending on whether we put a material in between those plates, we can roll them up. This is called the Swiss roll approach. We got to stick an insulator in there to do that. We'll learn a little bit more about that as we go. The fundamental formula that connects capacitors to their voltage and charge that's stored on the capacitor is this one right here, Q equals CV, where the charge, which by the way is measured in capital C, coulombs, we learned that last time, or a couple times ago, is equal to the capacitance, which is, capacitance, which is measured in capital F, which stands for farads, named after Faraday. And then, of course, we have our volts, measured in capital V. The reason this is really important to kind of keep straight is you can see up here, we're talking about Q, but that's measured in capital C, but capital C is measured in capital F. And there could be some confusion about what C is. Is C the capacitance or is C the charge? So you have to understand the distinction between the unit and the variable. Try to keep those straight in your mind. So that's our first formula that we need to understand. It has a relationship between charge, voltage, and capacitance. And on a capacitor, whatever amount of negative charge builds up on one plate, the opposite amount of positive charge will build up on the other plate. And we can charge a capacitor up with a battery and then use that capacitor to release and power something else in the circuit. This formula right here, we're actually going to take a modified version of it. If we come down to here, we're going to use the dielectric equivalent. This is a formula right here that allows us to determine how big a capacitor is based on its specific specifications. So first off, the capacitance will equal K, which is the dielectric constant right here, which is in a table. I think we're on the page that it's in. Let's take a look. No, it's next page. Right here on page 483, there's all the dielectric constants. With these K values is what we would use. So we can see the bigger the number, the more capacitance something is going to have. Epsilon naught is the permittivity of free space. It is 8.85 E negative 12. That's a set number that we use every time we have that epsilon naught. A, of course, is the area of the plates. Now that's of one specific plate. So you can think about a plate. It's got a lead coming off this way, and here's its partner plate. I'm trying to draw this three-dimensionally, so bear with me a little bit. We would want to know how big is this plate back here. How, its cross-sectional area. The bigger the area, the more capacitance something can have. And then last is D, which is the distance between them. Distance. How far apart are those plates? Now, as they get too close, we can, if you look at that D, the smaller the D, the bigger the capacitance. But as we get them too close, there is a point at which we will arc across and burn our capacitor up. And that's one of the reasons why we want to put a dielectric or some material between them that's going to allow the sensation of electricity to pass through to kind of connect the positive and negative terminal or positive and negative sides of the capacitor, but not actually let them touch, and so it builds up that strength. Okay, and so this is the formula that we're going to use. If you're using air or empty space between the capacitors, you can use this 1.0006, but typically in the problems we're doing in the text, we just use 1. It's not a vacuum, which would be better in some ways, worse in others, but it's a little bit less predictable because air, it depends what's in the air, what is the density, what is the nitrogen content. A lot of questions we could ask. We're going to pretty much just go with 1, assuming we're talking about a traditional capacitor. All right, last thing we need to talk about is energy storage. When we store energy in a capacitor, it looks like this. The potential energy in the capacitor is 1/2 QV, or if you use the Q equals CV formula to do some rearranging, you could end up with 1/2 CV squared, 1/2 QV, or 1/2 Q squared over C. All three of these versions are just different versions based on substitutions from Q equals CV. So capacitors, again, they're like batteries, but they release their energy quickly, you're building up positive charge on one plate, negative charge on the other. You don't want to get them too close or build up too much charge, or they'll arc across. But storage and energy in a capacitor is an efficient way to have quick access to some energy that you need, rather than a battery. And we use them all over the place. We use them in clocks if you want it to tick every second. The nice thing about a capacitor is that the load time and unload time is very consistent in any given circuit. So you put a battery-operated clock on the wall, and you hear that tick, tick, tick. That might be the movement of the gears, but what's driving all of that is a capacitor that is charging and discharging every second in order to force the tick to occur. All right, well, good luck, and we'll see you in class.